Hello everyone, welcome to the lecture again. Today we are going to discuss the stable and unstable equilibrium of rigid bodies. Let us understand it by an example. Let us say that a body is moving on a smooth curve which is in vertical plane. Okay. So, consider the motion of a body on a smooth curve in a vertical plane. Okay. Now, if the body is there on this vertical plane, then the body can be in equilibrium at this point, this point, this point or this point. Okay. So, let me write it down. The body can rest at point A, B, C and D, which are points of maxima and minima of the curve. Now, let us identify which among these points are the point of stable equilibrium. A body is said to be in stable equilibrium if, let us say, when slightly displaced from its equilibrium position the forces acting on the body tend to make it return towards its position of equilibrium. Okay. So, this is the definition. As per the definition, you can see that the stable equilibrium is those points wherein if you displace the body, then the body will have a tendency to return towards its position of equilibrium. Now, from here it is clear that at A and C, the equilibrium of the body is stable, because if you move the body away from these points, then it has a tendency to return to the same point. This is not the case for point B, because herein if you displace the body, then the body is no longer going to come back to the same position. Therefore, point B and D are the point of unstable equilibrium. Let me write it down. If when slightly displaced from its equilibrium position, the forces acting on the body tend to move it further away from its position of equilibrium. So, if we refer to the same figure, then point B and D is the point of unstable equilibrium. At B and D, the equilibrium of the body is unstable. Now, we can also have a neutral equilibrium. Okay. So, the definition is the following: if the forces acting on the body are such that they keep the body in equilibrium in any slightly displaced position. Okay. Let us understand it by an example. Suppose we have a flat surface and on this surface you have a body. Now, you displace the body slightly. In that case, the body will remain in the equilibrium. So, it will move, but again it will be in the equilibrium. In that case, this is called the neutral equilibrium. Okay. Now, what are the conditions for the equilibrium? A mechanical system is in equilibrium when the derivative of its potential energy is 0, because the potential energy has to be maxima or minima at the equilibrium. Therefore, its first derivative has to be 0. That means, dV divided by dq, where q is any generalized coordinate, equal to 0, and V is the potential energy. So, here let me write down that q is generalized coordinate. Okay. Now, recall from the calculus, for maximum its second derivative has to be negative and for the minima its second derivative has to be positive. Therefore, for stable equilibrium, your d2v over dq square must be larger than 0, that means it has to be positive, and for unstable equilibrium your d2v over dq square less than 0, that means it has to be negative. Now, let us use this concept to examine few problems. So, this is the problem statement of question number 1. A 10 kg block is attached to the rim of a 300 mm radius disc as shown. Knowing that a spring BC is unstretched when theta equal to 0, determine the position or positions of equilibrium and state in each case whether the equilibrium is stable, unstable or neutral. Okay. To analyze the equilibrium, let us look at the system. There is a rim of radius b equal to 300 mm and the mass m equal to 10 kg is held by using a spring. So, there is a spring which prevent the rotation of this disc and the radius of this inner disc is a equal to 80 mm. Now, it is given that the spring is unstretched when the mass is in the vertical position. So, therefore, when theta equal to 0, then the spring is in equilibrium. Now, we can find out how much is the stretch in the spring, because that will help us to find out the potential energy of the spring. So, let us first see in this position when this angle is theta, how much the spring has stretched. So, theta is given by S divided by A, wherein let us say S is the stretch in the spring. So, therefore, S will be A theta. Now, let us also find out how much is the potential energy of this mass m. Let us say in this instant the height of the mass m from the horizontal is h. So, we can find out how much is h. H will be b cos theta, because this radius is b. Now, we can write down the total potential energy of the system. So, total potential energy V is the elastic potential energy plus the gravitational potential energy. So, V will be half k into s square, this is the potential energy of the spring, plus mgh. And here note that I have write down the whole thing in terms of theta, because theta is our generalized coordinate. So, let us write down this s and h from these equations, so that everything will become in the generalized coordinate. So, V will be half k, s is a square theta square plus mg, h is b cos theta. Let us call this equation number 1, and with this equation now let us study the equilibrium. So, we know that for equilibrium my dV over d theta has to be 0, therefore, half k a square into 2 theta. So, I am differentiating equation number 1 minus mgb sin theta has to be 0, and this gives us sin theta equal to k a square over mgb theta. Note that the values of a and b and m, k etc. are given in the question. Therefore, from here you can find out that sin theta is 0.8699 into theta, and this gives you theta equal to 0 radian or theta equal to 0.9 0.02 radian, which will give you theta equal to 0 degree and theta equal to 51.7 degree. Now, let us look at the second derivative. So, let us find out what is d2v over d theta square. This will be Ka square minus mgb cos theta. Again, the values of A, B, M, etc. are given. So, therefore, this will be 25.6 minus 29.43 cos theta, and for theta equal to 0, you can put over here, you will see that d2v over d theta square becomes minus 3.83, which is of course negative. Therefore, for theta equal to 0, the equilibrium is unstable. Now, let us look at the case for theta equal to 51.7 degree. In this case, d2v over d theta square, again you can put it here, theta equal to 51.7 degree, and you will see that d2v over d theta square comes out to be plus 7.36. That means, in this case the equilibrium is stable. Now, let us look at another question. So, this is question number 2, and the problem statement is following. The ends of the uniform bar of mass m slide freely in the horizontal and vertical guides. Okay. Examine the stability condition for the positions of equilibrium, and it is given that the spring of stiffness K is undeformed when x is equal to 0. So, you can imagine this assembly. When this bar is going to move down, in that case this spring is going to stretch. So, therefore, this spring is preventing the bar to come down, therefore, it will be in, it can be in equilibrium, and we are going to examine what are the conditions on the equilibrium. So, first of all, we have to write down what is the potential energy of the system. So, the potential energy V will be, let us say I fix my axis over here. So, this is the level, and from here I am going to calculate the potential energy. Let us say this height is h. So, this is where the center of mass of this rod is. So, the potential energy V will be mg into h, and the spring is stretched in this case by a amount x. Therefore, the energy associated with the spring will be half k x square. Now, again the first thing is to write down these equations in generalized coordinate. Here the generalized coordinate is theta, because with theta I can identify what is the state of the system is, or where all the parts of the systems are. So, you can see here that if this is h, then h will be b by 2 cos theta, and x is b sin theta. Okay. So, let us put that in this equation. We will get V equal to mg b by 2 cos theta plus half k b square sin square theta. This is our equation number 1, wherein the potential energy is in the generalized coordinate. Now, for the equilibrium, we have dV over d theta equal to 0. So, let us differentiate equation number 1, we get minus mg b by 2 sin theta plus half kb square 2 sin theta cos theta equal to 0. Now, let us take sin theta outside. So, we have mg b by 2, this 2 will get cancelled with that 2 plus kb square cos theta equal to 0. This gives us sin theta equal to 0 and cos theta equal to mg over 2 kb. Now, to find out whether the equilibrium is stable or unstable, let us calculate the second derivative. So, d2v over d theta square will be kb square 2 cos square theta minus 1 minus half mgb cos theta. This I calculated from here. And for sin theta equal to 0, that means theta equal to 0, we have d2v over d theta square equal to kb square 1 minus mg over 2 kb, and for stable equilibrium that is d2v over d theta square has to be positive. For that, your 1 minus mg over 2 kb has to be positive. So, this has to be larger than 0, that is my k has to be larger than mg over 2b. Now, for unstable equilibrium, we have 1 minus mg over 2 kb, it should be negative, that is my k has to be less than mg over 2b. Now, let us look at the second case, wherein cos theta is equal to mg over 2 kb. We have d2v over d theta square equal to kb square. Now, let us put cos theta equal to mg over 2 kb. So, we will have mg over 2 kb whole square minus 1. Now, this quantity will always be negative because mg over 2 kb is nothing but cos theta, and the value of cos theta can not be larger than 1. Okay. So, therefore, this will always be negative, that means in this case the equilibrium will be unstable. Now, let us look at one more problem, and the problem statement is following. A light rod is pin supported at one end and carries a weight W at the other end. As shown in the figure. The ideal spring attached to the rod is capable of resisting both tension and compression and is unstressed when the rod is vertical. In the question statement, it has asked you to find out the largest value of W for which the vertical equilibrium position of the rod would be stable. So, the first thing is to write down the total potential energy of the system, and for that we have to find out the reference. In the figure itself, the reference line is given. So, therefore, let us write down what is the total energy of the system. So, U, which is the total potential energy, it will be the gravitational potential energy plus the elastic potential energy. Now, from the geometry you can see that the gravitational potential energy is W L cos theta, because in this situation the height of the weight W is L cos theta, plus the elastic potential energy. For that I have to find out how much the spring has stretched. So, you can see that in this situation the spring has stretched by this amount, and from the geometry I can find out this distance S equal to B sin theta. So, therefore, the potential energy corresponding to the spring will be half K into S square, and S is nothing but B sin theta. So, therefore, B square sin square theta. Also note that here this equation is in the generalized coordinate theta. So, now let us call it equation number 1 and find out du over d theta. So, this will be minus WL sin theta plus half K B square into 2 sin theta cos theta. Now, for the equilibrium, let us put du over d theta equal to 0. So, we have 0 equal to sin theta minus WL plus KB square cos theta, and this gives you that sin theta is equal to 0 or theta equal to 0, and this is the vertical equilibrium, and we were asked to analyze this case. Let us first calculate d2u over d theta square. So, that will be from here it will be minus WL cos theta plus KB square minus sin theta plus cos theta into cos theta. So, let me take first function, second function to differentiate it. And we know that for a stable equilibrium, this d2u over d theta square has to be larger than 0. So, therefore, we get KB square minus sin square theta plus cos square theta should be larger than WL cos theta, and let us put theta equal to 0 for vertical equilibrium. So, for theta equal to 0 we get KB square should be larger than WL, or my W has to be smaller than KB square over L. This is the condition for stable equilibrium in the vertical position. With this, let me stop here. See you in the next class. Thank you.